Hi folks, it's Dr. P. This video is going to get you acquainted with the Fluke Tabletop Multimeters. So this is the device that I'm referring to. The Tabletop Multimeter is basically the best tool that we have for measuring DC quantities of voltage and current. It is also the best tool that we have for measuring resistance. So let's talk about all of the different things on the panel, and then I'll do a couple of examples. First, we have our on-off switch, which is green. When you press it in, you'll see that the LCD screen turns on, which is an indication that this is working. If you press the green button and none of the indicators turn on, it probably means that this thing isn't plugged in. Along the top, we have a row of buttons, and then on the bottom we have our connectors. The button all the way to the left is for AC and DC mode. We usually always use this in DC mode. So when it's pressed in, it's in AC mode, and when it's out all the way, it's in DC mode. We use this for DC mode because in AC we have a better tool to measure voltages, and that is an oscilloscope. So we're not going to be using this for any type of AC circuit. The next three white buttons have to do with what mode this is in, and only one of these can be selected at a time. The green one is voltage, the pink one is current, and the mustard yellow is resistance. What you'll notice is that above the button itself, it tells you the units. So when I have voltage pressed, this thing is going to give me a number that is in units of volts. And when I press this, I'm going to have current measured in units of milliamps. And when I press this, I'm going to have resistance measured in units of kiloohms. Okay, so this helps us to understand and interpret what we're reading on the readout. The next 6 dark gray buttons have to do with the precision and the protection that we're going to be getting. All the way to the right-hand side is the least amount of precision that we can get on this tool. Why would we want to have a small amount of precision? Well, if we have a lot of current, a lot of voltage, or a high amount of resistance, then this thing is going to be able to kind of limit itself, so it doesn't get damaged by the amount of current or voltage that's flowing through this. Okay, so basically what we do is we get a trade-off. This thing can measure up to 10 amps. However, it's going to be giving us the least amount of precision on the readout. We're almost never going to be using this farthest right. Usually I like to start with the second one to the right. If I'm not sure what my readout is going to be, I like to start in a higher safety mode. And then if I need to, I can kind of move down to a higher precision mode. So again, all the way to the right is highest safety. To the left is highest precision. So why do we have this trade-off between safety and precision? Let's say that I have a fair amount of current flowing through my circuit and I want to measure it. And I have this on a high precision, low safety mode button. What can happen is the internal circuitry here is not protecting this device, and the fuse that's in here can blow. Right? The fuse blowing isn't the worst thing in the world because it's easily accessible, but it's best to not blow a fuse in the first place. So what I usually like to do is I like to start with this mode selected, especially when I'm measuring current. And then we can kind of go through and see if the precision can be increased. So I'm going to go ahead and connect up a circuit that measures current. Again, this tells me the units are in milliamps. So we can look at the connector plugs on the bottom to figure out which of these connections I have to use. This one says MA, or 8 milliamps. Okay, so this is the connector that I use for the input lead for current. This is our common lead, which is common for everything. And then this is our non-fused, this is our voltage and resistance measurement. Okay, so I'm taking my power supply, connecting it through the positive to positive. The common is going to go on my breadboard, and then I need one more banana plug to go from my breadboard back to the DC power supply. So what I have right now is 3.5 volts being applied to some resistive elements that I have on my breadboard, and I want to measure the current flowing through them. So as you can see, this readout on our multimeter is giving us a high amount of safety but a very low amount of precision. So right now it's telling me 2 milliamps, but that could be really anywhere between 1.5 and 2.4 milliamps, and I don't know what that is unless I increase the precision. So how do we know we can increase the precision? What we do is we look at the numbers above each of these buttons. So I'm going to look at the next button down, and that says 200 on it. So if my number on the readout is less than that number, which in this case is 200, that means I can safely press this button without worrying about damaging the multimeter. And what you notice is, as soon as I hit that button, my precision increased. Okay, so 1.5, that's vastly different from our reading of 2. So we definitely want to increase that precision if we can. To figure out if we can increase it even further, we can ask ourselves, well, is this number less than the next button down, right, which is 20? And because it is, I can press that, and now I get even more precision, right, 1.49. If I want even more precision, we can ask, is it less than 2? And it is. So look, we get even more precision as we go down. Okay, and again, with the caveat of less protection. So if I had 200 milliamps running through this, I certainly wouldn't want to be on this level of protection, because then I might blow a fuse. This is mostly an issue with measuring current. Usually because there's such a high internal resistance on this thing for measuring voltage, it's not as big of a problem there. How do we know if we have a good or bad fuse in our multimeter? If you kind of push onto the milliamp part and turn it counterclockwise, you will see that there is actually a fuse that you can remove from the circuit. And what you want to do is you just want to check to see if that filament inside the fuse is completely connected from one end to the other. If it is, then the fuse is fine, and you can stick it back into the supply or the multimeter and then just kind of turn it clockwise until it catches. If your fuse is bad, that's fine, just ask me for a new one. If there's a bad fuse, what will happen in your current measurements is that it will just read 0. This might lead to some frustration and head scratching as you ask yourself what went wrong to give you a current of 0. So if you see a current of 0 and there's no good reason for it, check your fuse. Another possibility could be that you are in voltage mode or resistance mode, or instead of using the specific lead that you have to use for current, maybe you're accidentally using this lead. So make sure you're using the correct lead. I always like to reset this thing back to 2000 in between to put it in high safety mode. Let's do a voltage measurement. As we know, voltage is measured in parallel over components, which makes it hard to screw this up, although it's definitely possible. So we want to make sure that our common lead is connected to the low potential point in our circuit, and that we use the voltage kiloohm lead for the high potential connection. What happens if we swap those accidentally? Well, in that case, we're just going to get a negative value. Similarly, as we saw with the trade-off between precision and safety for current mode, we can do the same thing for voltage mode. And I can go ahead and just kind of keep decreasing this until I hit a point where I get the highest precision. So I have a voltage divider on my breadboard, which I'm measuring. I have two nominally equivalent resistors. What happens if we go to a value that's too small is we wind up with this kind of error. It's not really an error message, but we get a 1 point, which doesn't really make sense. So if we ever see that, it means that our precision is too high in order for us to get an accurate reading. So we need to go up at least 1. If we continue to see that 1 dot, right, that means we need to kind of keep decreasing the precision until we get to a point where it's actually able to read. Last, we could measure resistance with this. So when a multimeter measures resistance, it actually supplies a voltage and measures the current that flows through. That means that this must be done in the absence of any voltage sources. So what I would want to do is I'd want to make sure that my power supply is disconnected from my circuit at that point. So if I try to do this with the power supply also connected, we are not going to get an accurate readout. We need to make sure that the resistance is selected. And then actually, because we measure resistance in parallel, we notice that this thing automatically went to measuring the resistance of this circuit. So these are 4.7 kilo ohm resistors. So we're reminding ourselves that this is measuring in units of kilo ohms. Okay, and again, if I were to start accidentally with too high a precision, we're going to get an error. And if we start with too low precision, we're just going to get a number that's not terribly accurate. So we always want to pick the value that is the highest amount of precision that we can get based on the value that we're using. Okay, and if I do 2 of these in series, right, then I can see the increase in the resistance. Until next time, stay well.